My name is Sophie McCabe, and today I will be presenting my findings from Lab 5. In my presentation, I will have 3 sections. The first is an introduction, where I will be discussing the purpose of the lab, the fundamental principles involved, and a summary of my results. Second, I will be discussing my data, measurements, and observations. Finally, I will be concluding my presentation with my answers to a few thought-provoking questions. The purpose of this lab is to apply Faraday's law to the example of a bar magnet falling through a conducting tube to model the resulting ring currents. To no surprise, the fundamental principle in this lab is Faraday's law, which states that a varied magnetic field, or magnetic flux in this case, due to a falling bar magnet, creates an EMF that can move charge or create a current on various current loops. These individual current loops are modeled by a column of circular aluminum rings created by wrapping a tube in foil. A brief summary of my results is that the velocity of the bar magnet increases greatly while the bar magnet is falling through the tube, and then in the model, the velocity plateaus. For this experiment, I used my phone to record a video of my bar magnet dropping through a tube wrapped around in aluminum foil. The tube is supposed to represent a tunnel of conducting loops designed to respond to the magnetic moving field of the falling bar magnet and exert a force on the magnet that is equal and opposite to the force that the bar magnet exerts on the infinite loops. My tube was 0.25 meters in length. My magnet had a mass of 0.0241 kilograms and a mu value of 3.022. I dropped my magnet through the tube 5 times and then averaged the time intervals to calculate that the average drop time was 1.8 seconds. I used this value then in my code. In the first part of my code, I inputted all of my observed values about my tube and my magnet, such as the tube length and width, into the code. I then created a function for the magnetic field of the bar magnet, which I pulled from my Lab 3 code. Next, I created a function for the time derivative of the magnetic flux, which I later plug into Faraday's law. Then, I defined the gravitational force, which only acts in the y direction. After that, I defined the ring current and then used it to calculate the magnetic force on the current loop due to the bar magnet using Faraday's law. Finally, I calculated the net force on the bar magnet and used it to update the magnet's position and velocity in the model. After I ran my code, I got a simulation of my bar magnet moving through the tube. Below that animated simulation is a graph of the bar magnet velocity over time. Initially, the velocity drops and then picks back up speed until it plateaus, most likely showing the bar magnet's acceleration to terminal velocity as it falls through the tube. The velocity then plateaus again for a few more seconds before dramatically decreasing. Since the magnet is not falling for that long in real life, I think that this is just a result of the model not always being the best representation of real life beyond the scope of its initial fall. So the model isn't necessarily useful for time past 1.8 seconds, which we can see because that's barely when the line starts to plateau, meaning that the magnet has just hit terminal velocity. Before I conclude, I would like to address 2 key questions. First, if the resistivity of the conducting loop was decreased to near 0, the magnet would take longer to fall because it would decrease the current flowing through the conducting loops in the tube. This thus increases the magnetic field opposing the charge in position of the bar magnet as it falls, thus decreasing its velocity. If the resistance was 0, the magnet would not be able to fall at all. Second, if holes were caught in the tube, the current would be obstructed. This decreases the opposing magnetic field and thus increases the velocity. Thank you for watching.